During the summer of 1977, a duo of Titan Centaur rockets, each transporting nearly identical spacecraft, was launched by NASA's Jet Propulsion Laboratory. Voyager 1 and Voyager 2, recognized as twin probes, were crafted to endure for 5 years, with the objective of examining Jupiter and Saturn alongside their larger moons. Astonishingly, nearly 45 years later, both probes maintain continuous communication with NASA. Routine commands are received, and the collected data is transmitted back to Earth's deep space network, establishing Voyager as the lengthiest-running mission in the annals of space exploration. Having accomplished all initial objectives within 4 years, NASA extended Voyager's mission to encompass the outer giants, Neptune and Uranus. Subsequently, the Voyager Interstellar mission was initiated, aspiring to explore the outer limits of the Sun's sphere of influence and beyond. Presently, Voyagers 1 and 2 have traveled 22 billion kilometers and 18 billion kilometers from Earth, respectively, arriving at the point where they departed the heliosphere and entered interstellar space. However, even for these long-lived Voyager probes, time is dwindling. Potentially by 2025, the probes may deplete their remaining power supply and permanently cease operations. In anticipation of this inevitability, NASA has commenced the process of deactivating the probe's instruments, with the aspiration of prolonging the mission's lifespan for a few more years. Nevertheless, when the Voyager probes inevitably cease functionality, they will leave behind an unparalleled wealth of data in terms of both size and scope. Approaching the final days of the Voyager mission, contemplation arises. What revelations did Voyagers 1 and 2 unveil out there? Did the probes and their instruments withstand the rigors of interstellar travel? And what surprises have NASA scientists encountered in their findings? While initially designated for a 5-year mission, Voyagers 1 and 2 witnessed the foresight of their team of scientists and engineers who, through various design choices, fortified the probes for an extended expedition. Each probe is equipped with a robust radioisotope thermoelectric generator, converting heat from the decaying plutonium-238 isotope into electric power. Furthermore, redundancies for most of their 11 scientific instruments and 16 hydrazine thrusters, including 8 backups, were integrated to address potential machine failures. Importantly, the launch coincided with a unique planetary alignment in 1977, occurring once every 176 years. This facilitated flybys of Neptune and Uranus with minimal course adjustments, providing the probes with a gravity assist from each visited giant. This maneuver increased their effective velocity beyond the capacity of their own rocket propulsion, a concept relatively novel at the time, previously attempted only on NASA's Pioneer missions to Jupiter and Saturn. In 1981, Voyager 1 veered from the ecliptic, Earth's orbital plane around the Sun, heading 35 degrees north. Simultaneously, Voyager 2 descended below the ecliptic, heading 48 degrees south. Following the expansion of the Voyager planetary mission into the Voyager interstellar mission, the cameras on both probes were deactivated to conserve power. The final image captured by Voyager 1 is the renowned pale blue dot photograph of Earth, seen from a distance of approximately 6 billion kilometers, the most distant image of Earth ever taken. However, this marked merely the commencement of the Voyager's odysseys. To reach interstellar space, the probes had to traverse the termination shock, a region where hypersonic solar winds encounter fierce resistance from the interstellar wind. Beyond the termination shock, the Voyagers encountered the heliosheath, where slowing solar winds accumulate, growing denser and hotter, followed by the heliopause, the ultimate boundary between the heliosphere and interstellar space. Contrary to common belief, the initiation of the interstellar medium doesn't actually signify the end of our solar system. Absolutely, another 300 years will be required for Voyager 1 to reach the Oort cloud, an extensive region teeming with billions of icy planetesimals encircling our solar system like a bubble. It will take an additional 30,000 years for the spacecraft to depart from the cloud, marking its permanent exit from our solar system. Amidst their journey through the heliosheath, the Voyagers stumbled upon a remarkable revelation. Thanks to the Sun's magnetic field, which spins in opposite directions at its north and south poles, these opposing spins generate a ripple upon meeting, recognized as the heliospheric current sheet, akin to the rings formed by dropping a stone in water. However, upon reaching the termination shock, the sheet undergoes compression, resembling the effect of ripples hitting the edge of a pool. The Voyager probes unveiled that beyond the termination shock, these amassed ripples evolve into magnetic bubbles. Consequently, the boundary of the heliosheath is not as smooth and well-defined as previously believed by scientists. Instead, It manifests as a fluctuating and magnetically bubbly environment. This messy revelation has necessitated a comprehensive revision of our model of the heliosheath. On July 25, 2012, the Voyager 1 space probe accomplished the historic feat of becoming the first human-made object to depart the Sun's heliosphere and venture into interstellar space. Traveling at a staggering speed of 540 million kilometers per year, equivalent to 3.6 astronomical units, AU, the distance between Earth and the Sun. It crossed the heliopause approximately 120 Australian dollars from the Sun. Interestingly, the exact location of the heliopause had remained unknown, with early models proposing its proximity to Jupiter or possibly much farther. The heliopause denotes the boundary where the Sun's solar wind encounters a halt due to its interaction with the interstellar medium, reminiscent of the collision of potent bodies of water. The solar wind comprises charged particles such as electrons, protons, and alpha particles emanating from the Sun, while the interstellar medium encompasses charged particles, gases, and cosmic dust originating from the Big Bang and ancient supernovae. Upon the collision of these charged streams, they modify their trajectories, giving rise to an equilibrium zone recognized as the heliopause boundary. Initially, NASA hesitated to confirm Voyager 1's ingress into interstellar space. However, the probe's plasma wave detector registered a notable increase in plasma density, 80 times greater than that in the outer heliosheath, and a surge in galactic cosmic rays. Intriguingly, the ambient magnetic field exhibited no noticeable alteration after traversing the heliopause, contrary to theoretical models predicting shifts in magnetic orientation within regions dominated by other stars. Baffled by this anomaly, NASA waited nearly a year before officially proclaiming Voyager 1's entry into interstellar space. On the 5th of November 2018, Voyager 2, with a slightly reduced velocity of 490 million kilometers per year, $3.30 per year, accomplished a comparable feat by entering interstellar space at a distance of 120 Australian dollars from the Sun. Analogous to Voyager 1, Voyager 2 detected no alterations in the ambient magnetic field. Scientists were taken aback, given that this traversal coincided with the zenith and solar activity during the Sun's 11-year cycle. Contrary to prognostications, the dimensions of the heliosphere persisted, posing a challenge to prevailing models. Approaching the culmination of the Voyager mission, the twin probes commence enduring cosmic odysseys. In an estimated 40,000 years, Voyager 1 is anticipated to meander towards AC plus 793888, a star situated in the Camelopardalis constellation, while Voyager 2 will traverse 1.7 light-years in proximity to the star Ross 248. In 296,000 years, Voyager 2 will draw near to Sirius at a distance of 4.3 light-years. These tenacious probes are positioned to outlast Earth, symbolizing human resourcefulness and resilience within the vast expanse of the Milky Way. Both Voyager probes transport a golden record, a gilded audiovisual disc featuring photographs of Earth, sounds encompassing whales and infants crying, compositions by Mozart and Chuck Berry, and salutations expressed in 55 languages. If they chance upon intelligent life, these records will proffer a glimpse into the diversity and culture of Earth. As we bid adieu to these audacious probes, we eagerly anticipate forthcoming cosmic ventures beyond the Voyager mission, delving into the profundities of space and embracing novel possibilities. Interestingly, while probes like Voyager have been dispatched into space, SpaceX has taken a stride further by dispatching a Tesla beyond the orbit of Mars in 2020, showcasing the notable strides in space exploration and technology. If you enjoyed our video, make sure to subscribe our channel for more content. Thank you.